test sites are increasing. 20, yeah, it is 26. 26 plus 5 these intermediates. So now it is going to happen 31 test sites are available. As sir told earlier, we are focusing on single stacked faults. I will tell, sir has already explained with the help of AND gate why single stacked faults are much more important, because at the same time they are going to cover multiple faults altogether. And because those are going to cover multiple faults altogether, so we only need to focus on single stacked faults, and most of the faults will be covered with the help of single stacked faults. So when we are considering the single stacked faults, how many total faults will be available? For one branch, we have two type of faults. One is stacked 0, another one is stacked 1. So stacked 0 or stacked 1 can be at any site. For example, here it can be stacked 0 or stacked 1. Likewise, any of these sites can have stacked 0 or stacked 1. And likewise, so if there were total 26 lines, fault sites, so the total single stacked fault, one at a time, at any particular branch, one fault at a time. So we will be having 26 into single stacked fault 0, single stacked fault 1. So those will be total 26 into 2. But now it has been increased to 31 into 2. So the number of single stacked faults has been increased. And if we talk about multiple stacked faults, definitely those have been increased. And that is the penalty we can have for that, right? So structural fault testing, basically it's beneficial because it is going to reduce our test vectors. And if the test vectors are reduced, then our total test time is also getting reduced. So that is the beneficial thing for this. Yeah. So in structural testing, what is the other problem? See, if I have the inputs and I have the output, I can control the input. I know what I need to put at the input. For example, I have a iron, and for iron, if I want to make it on, what I will do is I will make my switch on. So it means the current is going into this. Then how you observe whether the iron is working or not? You will identify this with the help of the indicator. If it is on, it means the power supply is going into the iron. And let's say now it is not working. So where is the fault? Definitely the fault is here. And if the indicator is not working, it means the supply is not connected properly. So it means there can be a fault from this wire to the iron wire. It is the possibility. There can be a problem. So this is the observation point. This is the observation point, and this was the input point. The plug was the input point. Now, in this, these were the inputs, 25 inputs. So we can control these. I want to put 0 or I want to put 1. It is in my hand. I can make the switch on or make the switch off. So 0 or 1 I can apply over here. Now what about the output? I can visualize whether it is output is 1 or 0 by connecting this to one LED. So if the LED is going to glow, I will say that this is 1. If LED is not going to glow, I will say that it was a 0. And I can observe that. Even though there was a fault, I can visualize that yes, the LED is not glowing and it was expected to glow. So it means it is a fault, or vice versa. So the fault can be at any place. But what about these intermediates? So these intermediates I cannot control from the input side, neither I can visualize these from the output side. These are the intermediate points, so we have to create the test nodes for that. So you can see over here, multiplexers are used because these are the fault sites. We need to forcefully force something to detect whether the fault was here or not. So we need extra inputs for this. We need extra inputs for this, and we need extra multiplexer. So this multiplexer is made up of, again, logical gates, and that is going to add the fault sites for this. So this is the penalty we are going to pay. It means much more complex circuit, much more multi-layer circuit, number of levels are increasing. It means we have to pay more for the test of that particular circuit. So that is the structural testing. And yeah, with the help of internal memory, that can be done. So related to how the internal memory will be working. So basically the inputs will go through the multiplexer. It will be forced to the next level. This is the bigger example, whether we used to have like a full adder, ripple carry full adder example is there. So the carry will always be rippling. So instead of passing the carry directly, the carry has been taken through the multiplexer, and the multiplexers are also having a test control. So with the help of this, the output of this multiplexer is either through the carry, which can be a faulty side, or it can be through a test control. So in order to figure out whether these carry inputs or intermediate input output sets are correct or not, we can use this test control and it will be working fine in that case. Yeah. So now let's proceed to the types of fault models. Sir has told multiple fault models. We will be taking mainly stacked fault models. There are three things basically you might have heard. Defect is one thing. Defect means any kind of imperfection we have, that is called as defect. Then fault. What is fault? If the defect is there in the digital circuit, we will call this as fault. So since we are talking all about digital in this course, so the defect and fault we will be using synonymously. And third one is error. So error happens especially in the simulation related things. Error is going to happen. And as we have discussed already, sir has discussed in the morning lecture, that the test is going to happen on the actual hardware. Actual hardware means is in your hand. After that you will be taking it for the testing, right? So the defect and faults are on the real hardware, while the error is in the software you can have. Yeah. So basically three fault models I have listed over here. Stacked fault model, where any of the branches is stacked at 0 or 1. It can be single stacked fault model or multiple stacked fault model. We will take one example to figure out how exhausting fault models we can have. Delay fault model and bridging fault model. So delay fault model will increase the input output delay, and in bridging fault model, end breeze or any kind of shorting which was not wanted, it may be metallic or something, that is the bridging fault model. So let us discuss exhaustive stacked faults in this particular two input AND gate. I hope my slide, my screen is visible, right? Is it visible?
Visible है मैंने.
Thank you, sir. So I can have 0 or 1 at input A. Likewise, I can have 0 or 1 at input B. And likewise for the third one, output, I can have 0 or 1 at output C. Now let us talk about single stacked faults. So single stacked faults are two types. One is 0 and another one is 1. So 0 fault can happen at, let me Yeah, so we will denote the single stacked fault by this. Single stacked fault, SA0 means single stacked fault 0, and single stacked fault 1 means single stacked fault 1. So this is A, B, and this is C. Likewise, single stacked fault at A, B, and C. So these are the possibilities. So how many faults are available? Single stacked 0 at A, B, and C. These are in numbers 3, and these are also in numbers 3. So total faults are 6. How many sites were there? 3 sites were there. So out of these 3 sites, we have to choose any one of the sites. So we will be having 3C1 into what is the type? The type is two types. We can have 0, 1, or we can have either 0 or 1. So these many faults, single stacked faults we can have, right? Likewise, if I want to figure out how many double stacked faults I can have, so I can have a combination out of these. I can choose one, and out of these I can choose one. But at the same time, I cannot have like a stacked 0 and 1 altogether at one branch. So single branch is mutually exclusive. So what I have to take? I have to take 2 combinations out of the 3. So the probability becomes like combinations will be 3C2 into. There are total 2 faults. So 2 faults can happen on one branch. It can be stuck at 0. Another branch it can be stuck at 0. One branch it can be stuck at 1. Another branch it can be stuck at 0 and vice versa. And it can be 1, 1. So how many combinations? 2 raised to power 2 combinations, because the faults are of 2 types and we have taken 2 sides, 2 lines. So it will be 3C2 into 2 raised to power 2. So this becomes 4 into this much. And likewise for the all 3 can have the faults. So we can have 3C3 is the total combination. And we have to multiply this with how many patterns of 3-bit is possible? 2 raised to power 3. So adding all these together, we will be having the total number of faults, which are stacked faults, single stacked faults and multiple stacked faults altogether. So to figure out that how many faults we can have, let me do the calculation over here. Let me take this rough base. Yeah. So we had 3C1 into 2 raised to power 1. We are talking about 2 input AND gate, okay? 3C2 into 2 raised to power 2 plus 3C3 into 2 raised to power 3. So this becomes 3 into 2, that becomes 6, plus 3C2 is again 3 into 2 raised to power 2, that is 12, plus 3C3 is 1 into 2 raised to power 2, that is 8. So 1 into 8 is 8 only, and this becomes 26. So this 26 I can represent it in this way: 3 raised to power 3 minus 1. So total number of faults, this was stacked 1, single stacked fault, double stacked faults, and this was triple stacked faults. So total number of faults will be represented by this formula. Generalized formula will be 3 raised to power k, where k is the number of lines. Okay, number of lines. So I hope you could understand that in the previous case where the total number of lines increased from 26 to 31. So the total number of faults actually increased. 3 raised to power k minus 1. It will increase by this fashion. So we will only focus on single stacked faults, because one single stacked fault will bring out many multiple stacked faults altogether, as sir has discussed just now in the last slides of his lecture. Yes. Based on this, we'll go with equivalence, fault equivalence based collapsing and fault dominance based collapsing. So what is fault equivalence? So fault equivalence is, by definition, fault equivalence is two stacked faults F1 and F2 are called equivalent if the output function represented by the circuit F1 is the same as the output function represented by the circuit F2. So it means we can take this example. Let's say I1 and I2 are 2 inputs and O is the output. Okay, we want to find out which 2 faults are equivalent. So what it says, stacked faults F1 and F2. These will be equivalent only and only if we are having the output function represented by the circuit with F1 fault is same as represented by F2 fault. So let's have a look. Let's say this is the single fault only. So in order to pass this fault at the output, what we need? So let me take the circuit again. So now I have a fault only at this place, and this is stuck at 0. So it means this fault is stuck at 0. So it means I can pass any input to B only. I cannot pass anything at A. So if this is stuck at 0, I am going to pass, let's say 1 over here. Why I am going to pass over 1 over here? If I am putting it 0, then irrespective of the fault at A, it is going to give me the 0 input. So 0 is known as the controlling input for the AND gates, because it is going to control its output irrespective of other inputs. So we will be calling 0 as the controlling input, and 1 is non-controlling input. 1 is non-controlling input, because if you are having 1 at the input, it doesn't matter that it does really matter what other inputs are, and then we are getting the output. So I am having 1 input, non-controlling input always we have to have at other inputs which are not faulty. So if this is the combination, let's say 0 is the, I'm going to apply 1, so true is 1 and faulty is 0. We are going to represent it in this way. So 1 means it is true and this is faulty. So in order to find out what will be the output, if it is 1 and this is also 1, then output I was getting 1. Okay, so it means fault free output was 1. But because of the fault stuck at 0, what I'm getting output 0 because of the fault available over here. So I will make 0 ended with 1. I'm getting output 0. So in the combination where A was 0, stuck at 0, what I'm getting at the output? I'm getting output C is equal to 0, 1. 1 is the true and 0 is the faulty. And what is the input required? 1 is the input required. That is going to excite the fault. Now let's say we are going to exchange the branch. Instead of A, we are going to take the same we are going to take the same fault at B. So let's say true is 1 and faulty is 0. So I am crossing this. It means it is true now. The fault is not there and the fault is here at B. Okay. So in this case, if 1 is there, this ended with 1, I'm getting 1. If 1 is at A, I'm having the fault at B, which is stuck at 0. So what is the output? It is 1, 0. What is the input in this case? Again, I'm having the input 1, 1. For B is stuck at 0 as well. And what is the output? Output is 1/0. And likewise, if I consider that the fault is at the output C. So instead of AB, let me have the fault at output C. So in this case also, I'm going to apply A is equal to 1, B is equal to 1. And what will be the output? Because it was stuck at 0. So irrespective of 1, 1 input or any of the input, I am having 1, 0 output. 1 was expected, true, but 0 I am getting. So what are the combinations for all these 3 faults? Whether A is 0, B is stuck at 0, C is stuck at 0. The input patterns are required, which are same. 1, 1 are the input patterns. And what is the output? At C, which is the output node, I can see that the output is true is 1 and faulty is 0. So it means the input is same and output is same for all these 3 faults. So this is known as fault equivalence. This is known as fault equivalence, means all these 3 faults are equivalence. Now equivalence based collapsing, what it says, out of these 3 faults, I can have any one of the fault. Out of these 3 faults, I can have any one of the fault. Now which fault I should have, that will be decided by the test vector. So we have to choose the test vector. If, let me proceed. So these 3 faults are, these faults are equivalent faults. These faults are equivalent faults for AND gate. These are equivalent faults. Likewise, for OR gate, we can have stuck at 1 faults which are equivalent, because we have the non-controlling for OR gate is 0, right? Non-controlling input is 0 and another one is stuck at 1. So we were expecting 0, 0 input and output we were expecting 0. But since stuck at 1 fault is going to make it 0/1. like that. Likewise, for NOR gate, we have stuck at 0 faults at the input are equivalent to stuck at 1 fault at the output. Why? Because, for example, let's say this is the fault. What I need over here, 1 at the input, 1 at the input. What will be the output? I am expecting 0 at the output. Okay, so this 0, what it can detect? It can detect 1. It is just like LED. 0 is LED off, 1 is LED on. So if the LED is off, I'm getting, so it means previously it was expected to be on. So it means it is going to, if the output is 0, so it means it is going to detect the fault. I have written it reverse. 0/1 it will be. 0 is the true value and 1 is the faulty value. So that's what output stuck at 1 fault is equivalent to the stuck at 0 at the input faults. Likewise, for the NOR gate also, we have input stuck at 1 faults which are equivalent to stuck at 0 at the output. So both of these you can check the output because it is inverted. So the fault is whatever is stuck at 0 was at the output, that is stuck at 1 at the output for NAND gate. And likewise, it is inverse of each other output, and at input, these are the same fault sets which are equivalent. What about NOT gate? So single stacked fault 0 at the input is equivalent to single stacked fault at output, single stacked fault 1. And likewise, vice versa, single stacked fault 1 at the input is equivalent to single stacked fault 0 at the output. Okay. So now fault equivalence for single stacked fault models, we have the cases of fanouts and stems. So here, this is the fault site. This fault site is having 2 outputs, 1 and 2. There are 3. This fault site is going to take this path to reach to this output, and this fault site is going to take this path to bring the output over here. So you can have the fault over here, here, and here. There are 3 lines, fault sites. There are 3 fault sites. But these 3 fault sites will have the same input. Of course, if this is 0, then I have to apply 1. The input is same for each and every one, right? What about output? If this was the fault, then what is the output? I am getting output 0 over here and 0 over here. But the true output, I was expecting 1 over here and 1 over here. Okay. Let's say this output is x1 and this output is x2. So likewise, x1 over here, I'm getting the fault size. Look at this, fault size is this. So I'm getting true value is 1 and faulty value is 0. But over here, true value is also 1 and faulty value is also 1. That means there is no fault. So it means these outputs are not same. Inputs are same. Faults, if I am putting at another branch, the outputs are not same. By definition, fault equivalence says that the definition of fault equivalence says that the set of inputs corresponding to each and every fault is equal to the set of outputs. But the set of outputs are not same. Now, the same thing let us apply for this. So in this case, third case, I have stuck at 0 over here. What it says that the true output is expected to 1, but because of this fault, I am getting 0 over here. Here the true output and the faulty output, because there is no fault propagating through this branch, so I am getting 1 1. So here also these 3 outputs are not matching at all. Okay, and the lower 3 extra outputs are not matching. So we'll say that the stems are not equivalent. The faults on the stems are not equivalent. Please make a note of this. So this is the fault equivalence. By definition, this is the fault equivalence. Now, fault equivalence based collapsing. By definition, fault equivalence based collapsing, what we can do, the number of faults which are equivalent, we can represent those by one of the fault. Okay. So for example, in AND gate, the 3 faults were equivalent. So you can keep out of these, you can keep maybe this one only. Why I have chosen this? The reason for this particular fault, let's say it is A. So you can have 1 0 is the input combination. 1 1 is the input combination. For the next one, 1 1 is the input combination. If output is also stuck at 0, then Also you have 1 1 as the input combination. All input combinations are same, so you can have any one of these three. So I have cut these two and I have kept this. Likewise, fault equivalence for this, I am going to cut, let's say, these two, and I kept this only. Now let's say OR gate. For OR gate, the by definition equivalent faults were stack at 1. So I will cut this fault and this fault, and now I am left with this fault set. So total number of faults were the number of branches. So number of branches were 1, 2, 3, 4, 5, 6, and 7. 7 into the types of faults, stack at 0 and stack at 1. Total number of faults were 14. Because of fault equivalence, we have applied the fault equivalence in this case. So how many faults reduced? 1 and 2 from here, 1 and 2 from here, 1 and 2 from here. So I have reduced 6 faults. So now the number of faults are reduced. 14 minus 6 is equal to 8. So just because of equivalence base collapsing, I have reduced the faults to 8. Now, let us consider, fault equivalence base collapsing. This is the circuit after fault equivalence base collapsing. So now, let's have the example for stem case. So this is the case of fan out. Here, this is the stem, and then there is the branching. So we know that the stems are branching are not having any fault collapsing, fault equivalence based collapsing. Only AND gate and OR gate we can collapse the faults. In AND gate, I can reduce these stack at 0 faults. For OR gate, I can reduce stack at 1 faults. Let's say I have reduced this one. So now the number of faults available are 1, 2, 3, 4, 5, 6, 7, 8. So now the number of faults available are 8. And how many branches were there? 1, 2, 3, 4, 5, 6. 6 branches. So total number of faults were 6 into 2, 12. So out of 12, we have reduced 4 faults. So we are left with 8. Okay. So likewise, fault equivalence based collapsing can be applied for logical gates. And this is with the stem example or fan out example we have taken. If there are multiple fan outs also, then the rule for that also will be similar. Whatever we have 2 fan out, n number of fan outs, it will be similar to that. So this is the example, the final result for fault equivalence based collapsing for this fan out based circuit. Now, next one in the list is fault dominance based collapsing. So what is dominance? Dominance means some fault which is dominating. So by definition, it is like this. If all tests of stacked fault F1 detect a fault F2, then F2 dominates F1. Means faults of 1 are subset of fault F2, fault patterns of F2. Then F2 dominates F1. If F2 dominates F1, then F2 can be removed and F1 can be retained. That guarantees that, of course, if we are supplying this set of test vectors, then F2 will get detected. So let's take the example of AND gate, 2 input AND gate. So here we have taken the example of stack at 1 fault. This is stack at 1, and stack at 1. What input test vector is needed? So in order to figure out the stack at 1 over here, I need 0, 1. Here I need 1, 0. Here I need 0, 0. Okay. So along with 0, 0, I can also have 1, 0 or 0, 1. So it means what? It means that this fault F2 output fault stack at 1 dominates this fault and this fault as well, because this is a superset. This is, let's say, output C. So output C is a superset of, this is, let's say, input I1. It's written I1. So it is I1 and it is I2. So we can remove the fault if we are sure that if applying this test vector, I am able to detect that fault also, which I am going to remove. So if I'm using this test vector, then I can make sure that this fault, the C fault, is also being detected. So it means F2 here is C, F1 here is I1 and I2. So I have to use I1 and I2, and I will remove C fault, so that, because the C is dominating. You can see this, the test vector for C is the superset of the test vector of I1 and I2. So you can remove the C and you can have I1 and I2. That is known as the fault dominance based collapsing. So we are running, the time is over as such, but I just want to cover this particular topic. So please bear 10 more minutes. I will try to cover by 1:10. Yeah, so this is fault dominance based collapsing. Here this fault I can remove. Likewise for OR gate, whatever is stuck at 1 over here, that is converted to stuck at 0 over here. I can remove this. For NAND gate, I have stuck at 0 at the output, which is dominant. Please make a note of it. It is stuck at 0 at the output, which can be deleted. And likewise for NOR gate, it is stuck at 1 at the output, which can be deleted. Okay. Yes. So this is fault dominance based collapsing. We can continue our previous example. In our previous example, we have reduced this stuck at 0 fault because of the fault equivalence based collapsing. And likewise, this is stuck at 0 also, this is stuck at 0 also. And this stuck at 1 at the output, and this branch we have reduced because of the OR gate stuck at OR gate equivalence based collapsing. Now we are on dominance based collapsing. So what dominance based collapsing says? Dominance based collapsing says that I can remove the fault if that is going to use the superset for the other F1 faults. So what is the superset? For AND gate, we found that this is the AND gate. These two faults are actually F1, and the output stuck at 1 is F2 fault. So output was anyway already was not there. So there is no need to cut down. These two faults stuck at 1 actually will be covering this fault, so I can remove this portion. Likewise, the output stuck at 0 can be removed because this is fault dominance as compared to this as stuck at 0 and as stuck at 0 at G3. So with the help of these red colors were already removed. Now I have removed this because of fault dominance, this because of fault dominance. This was anyway already removed, so there is no need to remove it again. And with the help of this, how many faults are available with us? So these are the number of faults available with us. Yeah, so we have removed this also. We are left with these faults. So here, what we can infer, we can just figure out how many faults are remaining now. So these are 4 stuck at 1 at the input and 2 stuck at 0. Total 6 fault out of 14 faults are available. Total 6 number of faults are available. Okay, so if we just check the inputs, there are 4 inputs. If at inputs only, if I just want to present the all single stacked faults, then how many patterns will be available? 4 into 2 means 8 patterns will be available. We can visualize that 6 is the number which is left is actually lesser than the 8 numbers which were available only at the inputs. Okay, so this is after fault dominance and fault equivalence based collapsing. Similar thing we can repeat for our example, which was with fan out. So in this, fault dominance based collapsing says that this stuck fault is also no more. So we can remove this stuck fault. If we are removing this stuck fault, because stuck 1 was already removed from here because of the fault equivalence based collapsing of this OR gate. So reducing this, we are left with these number of faults. So how many faults are available now? 1, 2, 3, 4, 5, 6, 7. 7 number of faults out of 12 faults are available. Out of 12, 7 number of faults are available. If we look at the inputs, then there are 2 inputs, 1 and 2. If we look at the branches, fan outs, then these 2 are the branches. We will be treating those also as the inputs. So 2 plus 2, we will be considering 4 are the checkpoints. Inputs are the checkpoints. And then these fan out branches are also the checkpoints. So there are total 4 checkpoints. So we can presume 4 into 2 can be the total number of poles, because and 7 is lesser than this number. So this is the checkpoint theorem. What checkpoint theorem says that a circuit with no fan outs as stuck at 0, stuck at 1 fold is to be considered only at the primary inputs. So in the fan out free circuit, the total test patterns will be 2 into the number of primary inputs is the total test pattern generation. For the circuit with fan outs, the checkpoints are primary inputs plus the fan out branches. So we'll be having the total test patterns 2 into the checkpoints. Okay. So for example, in this case, these were the 2 inputs plus these were the 2 fan out branches. So 2 plus 2 into 2. That is the total number of test patterns. That comes to be 8. So that is the maximum possible. That is the maximum possible single stacked faults available in any circuit. Likewise, in the previous case, there are 4 inputs. So there is no fan out in this case. So 4 inputs into 2 types of stacked faults. So total 8, maximum number of faults available can be 8 in this particular case. So this is the checkpoint theorem. So yeah, it is done from my side. I have covered the fault dominance based collapsing and fault equivalence based collapsing and the checkpoint theorem. The checkpoint theorem says that all the faults available in any kind of combinational circuit can be reduced to the input branches and the checkpoints. Only at the checkpoints it can be reduced. Checkpoints are input branches plus the fan outs are the checkpoints. And the total number of fault sites can be considered as checkpoints, and total number of faults can be considered as 2 into checkpoints. That is reduced. The total number of faults, which was explicitly 3 raised to power k minus 1, we have reduced to this much. Let's say it is 2 into the number of inputs. We have reduced that to this much. So this is all from my side. If you have any query regarding this, please feel free to ask. So there were multiple stacked faults. Those multiple stacked faults, we figured out that multiple stacked faults can be covered with the help of single stacked faults only. So this number we have reduced first of all to 2 into the number of branches, 2 into the number of branches, and from there 2 into the number of inputs, because inputs are even lesser than the branches. For example, in this particular case, what is the k number? These are the 4 branches, 5, 6, 7. So total number of faults available, single and multiple stacked, are 3 raised to power 7 minus 1. Total stacked faults, single stacked faults, we have 2 into 7. Okay. And inputs were 4. So the total number of faults maximum can be possible with the help of equivalence or dominance based collapsing. It can be reduced to 2 into 4. It can be reduced to max 8, and we have reduced in this to 6. This is a particular circuit. In some other circuit, maximum it can go up to 8. Yes. So if you have any query, please feel free to ask. Yes. In example, how you removed a stacked fault. Okay. In fault equivalence, fault dominance, how I have removed. Okay. So let's have a look at this. Fault equivalence, by definition, what is the fault equivalence? Fault equivalence is if I have equivalence based collapsing, we will be doing. If the faults are equivalent, we will remove all, but we will keep one. So we have taken the example of AND gate. If I have the faults stuck at 0 at A, B, C, any of the branch. Okay. So in every case, I need 1, 1 as the input, right? And since it is stuck at 0, so of course I want stuck at 1. I want 1 as the true output. So output will be 1 0. In every case, I will be getting output as 1, which is the true, and 0 is the faulty. In all these three cases, right? So it means what? These A, B, and C. A, B are the inputs and C is the output. All three faults are equivalent faults. If all three faults are equivalent fault, I can keep any one of them and others can be removed. Now, generally the output fault we have to remove. The reason being inputs we can control. Input is in our control. So inputs, we will try to push the faults towards the inputs so that it is easy to push that to 1 or 0 very quickly, right? I cannot expect that in a complex circuit output can be 1. I cannot expect, but easily I can expect I'm saying hardness, yes. So in the input, this is the easiest possible that I can make that 0 or 1, whatever I want to make, because that is input is in our control. Output I can just observe. So that is easy to observe. Input is hard to observe, right? So because of that, I will be reducing the output fault instead of input faults. So equivalence based collapsing, what I did, for example, this was the circuit. So in this circuit, by definition, this let's consider this. So stuck at 1 fault for OR gate are equivalent. So I can reduce these 2 faults and let's keep this only. Okay. So if I am removing these 2, I am keeping just one only, this one only. So my circuit is now it in this way. Likewise, fault dominance based collapsing. In fault dominance based collapsing, what we have to do is we have to make sure that a fault which is having a bigger set of test vectors. For example, we have taken the stacked fault in the stacked fault in AND gate. So this is the AND gate. Stacked 1 fault at the AND gate. Stacked S/1 means this is stacked 1. S/1 is stacked 1. So this is stacked 1. Yeah, this is stacked 1 fault. And here I have to apply 0. If I'm going to apply 0 over here, I was expecting 0. But since it was stacked 1, so I'm getting 1. So 0, if I'm applying 0 here, I have to apply 1 to the other branch. I have to check where the fault is existing. So first of all, let us consider the first fault is existing. This fault is existing. So in this case, I have to apply 0 and this was fault free. So 0, 1 is the combination. 0, 1 is the combination I have to apply for this particular fault. Let's say this is for I1 input. I1 input stuck at 1. Likewise, let's say this is I2 input stuck at I2 input is stuck at 1. This one is stuck at 1. So this was the fault free. So I have to apply 1 over here and 0 over here. What will be the output? The output is expected to be 0. But because it was stuck at 1, so I'll be getting 1. So yeah, this is I2. What about this stuck at 1? So the inputs were not stuck at faults. Inputs were fault free. And now I am going to apply the fault at the output. Stuck at 1 fault. So here I have to apply either 0 0. If 0 0 I am going to apply, I am trying to force this stuck at 1 to 0, right? But if it is faulty, I will be getting 1. So again, I am getting the output same in all these three cases, I1, I2 or the output. I am getting 0 1 as the output. Okay. If I am going to apply 0 1, I am expecting 0 output, but I am getting 1 output. That is erroneous. Likewise, if I am making input 1 0, then also I am having 0 1 as the output. So output is 0 1 in all these three cases, right? But the inputs are, for example, I1 is having common input as the output could have. I1 is stuck at 0 is having the same input, one common input. That common input is what? That common input is the subset of what C stuck at 1 can have. Okay. Likewise, I2 can be detected and C1 can also be detected with the help of 1 0 input. So it means what? I can remove C1. I can remove C1 as the fault dominance because it is C1 is dominating. You can see it is the test pattern of C1 is superset of I1 and I2. So it C1, and if I am having I1 or I2 in both of these cases, I am able to detect a C1. But there is nothing common in I1 and I2, so I cannot reduce these faults. So in fault dominance based collapsing, we have discussed the same thing and we have reduced the faults by the same way. This was the fault dominance based collapsing. So for example, let us take the example of OR gate only. So this is the OR gate. In this OR gate, because of the fault dominance, stuck at 0 can be reduced. In AND gate, this stuck at 1 fault can be reduced. This stuck at 1 can be reduced because stuck at 1 in AND gate at the output is dominating both of these faults, right? Like stuck at 0 at the inputs are being dominated by the output stuck at 0 of this OR gate. So because of that, I can remove this fault at the output. Okay. I hope it is clear to you, Mr. Sai Kumar. I hope it is clear to you. Yes, any other question? If there are no questions, let us make it off for the day. Let us conclude the session. And the evening session is going to start at 6 p.m. to 8 p.m. It will be started. And today's session will be taken by Professor Ravi Kumar. So it will be really nice session. So I request every one of you to join on time and get benefited out of this. It is really a good course. So yeah, it will be very beneficial. So thank you so much and happy learning.
Thank you, ma'am.
Thank you, Menka.
Thank you so much, sir.